Okay. So given f of x equals x squared, we're asked to find f prime of x. This is a situation where we're finding the derivative function. There is a function that will give every derivative of x squared at different values of x. Over here, this is a derivative value, which implies that we're going to use the derivative function and find the value of that at x equals 3. Sometimes this confuses students. You think you're going to substitute first. F prime of 3 basically means, hey, I want you to find f prime of x, and then I want you to find the value of that at x equals 3. So there's two different things we can do when we start with a function and we talk about the derivative. We can find a derivative function, and we can find a derivative value. Now, we're not going to work these out, but I'm going to write them. If I was going to find the derivative function, I would do that limit for x squared. So I would do the limit as h approaches 0 of x plus h quantity squared minus x squared all divided by h. Okay. I'm not going to do it, but if I wanted to find the derivative function, I would be using the limit definition of the derivative, but the f function would be what this function is. This function says that I want to work with x squared, so I will take my x plus h and I will square it, and I will subtract from it the function, which is x squared, and divide that by h. I'll expand that all out and take the limit and figure out and my result will be a function answer. Actually, I totally lied. Let's do that. I lied. Let's do that. I think this is a good place for us to start. So, may not get to the very end of the notes, but that's okay. This is more important. Okay? So, I have the x squared function. I want to find its derivative function. Yeah, you'll need your own paper. So the derivative function, I'm going to do this limit. Remember, there were two versions of the derivative finding limit. I'm going to use this first one. Let you get caught up with that.
Can we expand that out? Right?
So we're going to have to expand that out, yes. That is ultimately what we're going to do. So if you're ready and you've got that written down, why don't you see if you can do that? What will happen when you expand out x plus h, quantity squared, oops, sorry, let me do attendance real quick. And if you're sitting with a pre-calc honors background or some other background where you You're like, I know how to write the derivative of x squared. Okay, so then that means you know what should happen when you do that limit. You know what the end result should be. Let me see where we are on numbers today. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Perfect. Excellent. We are good to go. Okay. Here I go. With all my calculus skills. Lying, I'm just going to do algebra. X squared, 2xh, h squared. That's what happens when you FOIL x plus h times x plus h. Minus x squared, all divided by h. All right, that is that right there. If you think that's x squared plus h squared and it doesn't have a middle term, you have convinced yourself of something that's incorrect. When you square x plus h, you do not just get x squared plus h squared. So, the limit as x approaches 0 of 2xh plus h squared, all, oops, I left the h off. The x squareds divide off, or add out, sorry, and so it's 2xh, did it again, plus h squared, all divided by h. How do we find that limit? Yeah, when we substitute a 0 in for h, this is going to be 0 over 0. That means it still doesn't have a value that's apparent. But if you factor out an h, and then take the limit, what is the derivative function for x squared? What do I get when I take the limit as h approaches 0 of 2x plus h? Oh, you guys are making me sad. Right? 2x? No? What? Yes? Okay. We all okay with how I got 2x? Okay. How many people already knew that the derivative of x squared was 2x? Yeah, I don't have a problem with you already knowing that. And some of you are like, I didn't know. Well, by the end of class today you will, because that's actually really easy. You'll love it. The derivative of x squared is always going to be 2x. Okay. All of the stuff we had to do here with the limit definition of the derivative gets eliminated by a certain amount of shortcuts. So, find the derivative function from an x squared is get me 2x. Find the value of the derivative at 3. Now I'm going to go a little shortcut here. Since I know since I already on this side did that f of x squared, for f of x equals x squared, that f prime of x is equal to 2x, f prime of 3 would be 2 times 3 equals 6. Okay. Now, a really good exercise to do would be to work out that limit for the function x squared to see how that limit this limit is actually the derivative of f of x at x equals 3 when we replace f of x with x squared. Let's do it. Keep talking about stuff being a good idea, and then let's just do it. Okay, so this would be, but here's this is kind of a really good example of what I'm talking about. See, you've got to make sure, oops, come back, Mr. Limit Problem. Okay. Watching me do the thinking and the writing and you copying is not the same as you thinking about it yourself. Okay? You starting from the beginning. Okay? So as we work through a problem like this, and I talk to you, I give you this and I give you this, and I talk to you about all the thinking that we're doing, how we did this one way, and now here's me doing this an entirely different way. Okay, I got x minus 3. I used the other version of the limit definition of the derivative. So I used the f of x minus f of a over x minus a definition. I find that to be the easier one when I want a value. Okay, so I'm showing you both examples. So f of x minus f of a over x minus a becomes the limit as x approaches 3 of x plus 3, because this becomes x plus 3, x minus 3 divided by x minus 3. The whole cancels out. Oh, can't move that closer together. Just prettier. X minus 3, right? So x plus 3 and x minus 3 are my factors. X minus 3 here. The x minus 3's divide out, and there's the 6. The limit definition of the derivative will get you the answer. It'll get you the derivative function. It'll give you a derivative value, but it's a lot nicer to use a shortcut. I'll repeat myself. If you did not practice this at all from last class, if you did not go into the textbook to the problems and try using the limit definition of the derivative to calculate the value of those derivatives, then you're missing something that you're essentially going to be assessed on. So I recommend you practice it. Or if you tried to practice it and you struggled, you and I should be having conversations. Okay, so that we don't have to do all of this all the time, every time we want a derivative function or a derivative value, we've got some shortcuts. Newton, Leibniz recognized a variety of different shortcut scenarios, different things that always happen when we're working to take a derivative. The more we know these, the easier finding derivatives are going to be. Four basic rules to start off. The first one is if I have a constant function, the derivative function for any constant function is just the function y equals 0, or the value of any derivative of a constant function is 0. So if my function is f of x equals 5, and I ask you for f prime of 3, Well, for f of x equals 5, the derivative function is the constant function y equals 0. So that would mean that f prime at any number for that function would be 0. So if you have a constant function, the derivative of a constant function is always the function y equals 0. If you have a power function, essentially any x to an n, any x to the n, if we apply the limit definition of the derivative and we go through the process to find the derivative function, the resulting derivative function is always going to be equivalent to n times x to the n minus 1. So if we had the function f of x equals x cubed, its derivative function would be 3 times x to the power of 2. Bring the exponent, and this is it's a shortcut trick. This is the result that happens. For any x to the n, its derivative is 3 times x to the n minus 1. Okay. And if I put a constant in front of that function, then my derivative will just be the derivative of the function times that constant. And I'm going to write an example of that on the next page. A constant times a function, and I want the derivative of that combination. It's the same as the constant times the derivative of the function. So that means when I have f of x equals 7x to the 4th, that f prime of x, its derivative, would be 7 times, and I'm going to make a little note here. What are we going to do? We're going to take the derivative of x to the 4th. And what would I write for the derivative of x to the 4th? 4x cubed, correct. So the overall result, the derivative for 7x to the 4th would be 28x cubed. If we want to see like a proof of that, I am absolutely not going to do it, but we can run the limit definition of the derivative for 7x to the 4th. It'll be ugly because I'll have to do x plus h to the 4th power. I'll have a big expansion to do. I can do it though. I'm not going to do it, but I can, and I'm happy to write it out. If you want to see it proven, I'll write it out and send it to you. Limit definition for this, if I did the limit as h approaches 0 of 7 times x plus h to the 4th minus 7x to the 4th, all divided by h, the result that would come out of it would be 28x cubed. Super awesome that we know that, and we don't have to run the powers. Because like a 4th power, not pleasurable but doable. What if I made that a 10th power or 20th power? That amount of foiling isn't going to happen. Like, that's just not. But Newton proved, he could prove pretty easily, because he was Isaac Newton, that when we have a power function, that this kind of pattern was going to generate for the derivative. That our derivative function would be 1 degree lower, and that ultimately whatever constant we had we would end up with that constant and a product of the original exponent. the last rule on this page is the fact that if we have 2 or 3 functions added together or 2 functions subtracted, if we have functions connected by sums and differences, we can take, and we want to take the derivative of that sum and difference, we can take the derivative of each individual piece. So when I want to find the derivative of a big polynomial, like 5x to the 6th minus 3x to the 4th plus 2x to the 3rd minus 8x squared plus 17, I can basically think about this, since they're all being added and subtractive, I can think about x prime of x, f prime of x for each term, and then put them together. So let's see. And at the same time, I'm going to use my little constant rule. Okay, take a minute, see if you can figure out what that derivative is going to look like. If you thought about each term, about writing the derivative of each term, and each of those terms has a constant times a power of x. My derivative is ultimately going to be the sum of 4 terms, technically 5, but one will be 0. And the largest degree term will be a 5th power. Yep, what's the derivative? Because that goes back to our very first rule. If we're looking at the function f of x equals 17, its derivative is 0. Okay? So this is going to be 30x to the 5th minus 12x cubed plus 6x squared minus 16x, technically to the first, and then also technically plus 0. We usually don't write the plus 0 because we're lazy and sloppy. There we go. That is f prime of x.
We don't simplify that though.
How would you simplify that?
Like you take the constant multiple rule and then the power rule and do it again. Just like
Why would you?
to like bring the degree lower. You would do that.
Well, if the question is find the derivative, that is the derivative. There may be a question later that says find the second derivative. And so then, yes, we might go from here and then do that one more time. So what we would do, as far as the question, which is write me f prime of x, the first derivative of that function is those 4 terms. All right, now, here's a good kind of thing. Y'all don't say a lot to me. So right now, I need you processing how we got from here to here. And if you don't understand where I got every piece of that answer, your hand needs to be up asking me. Whether that's just to repeat it, and if you're like, I can't do that, what if I'm the only one? Who cares? You're the only one getting your grade, right? So everybody's 100%, 30x to the 5th, 12x cubed, 6x squared, 16x. We're all 1,000,000% good. Okay. Now, let's talk about question 2. You have to figure out what question 2 is about. Why is question 2 the next question we're doing? It's not random. There's a reason this question is next. Johnny, go ahead. Almost. What did you said the derivative is the tangent line. Almost, you need one more word in there. The derivative is the slope of the tangent line. Yes, that is exactly why this question is here. When did I teach you that the derivative was the slope of the tangent line? Last class. Yeah. Slope of the tangent line is code for derivative value. If you don't know the code, then you can know how to do derivatives all day long and it won't help you because you won't know that that's what you were supposed to do. Sometimes that's what happens to us. We can do certain things, but we don't know when we're supposed to do them. Slope of the tangent line means derivative value. All right. Now that you know that, find the answer to this question. Find the value of the derivative of f of x when x equals 1. And since we just discussed, I'm going to actually write down the much nicer way to say that. More direct. And when you finish number 2, take a look at number 3. Because it's in the same family of questions. Yeah, I gotta write you pass. Yeah.
This will run really quick. Is this right?
Yeah, right. Right. There we go. Here, take that. Wait, she comes back.
Did I do this?
Oh, wait. Do you have a question about something else, or did you decide you? Okay, hang on.
Did I do this right?
So you wrote your derivative, and you plugged in 1. Yes.
You want me to show you why and how I got this? Yeah. Okay, I didn't get 5. So, we had to take away the degree of this. Since the degree is 1, wait, 1 minus 1.
Help for.
Yeah, it's 0, so it's negative 5 times 1, so it's minus 5. The constant
Oh,
is
help for
0.
what we talked about on Tuesday? Yeah.
You
You
get
want to
it?
say
Yeah.
today? Yeah, sure, a little bit. Yeah, I
Sure
can't
you
stay
want-
past 4 today, but.
Wait, we got 0 there. Okay, now we got 0.
Yeah.
Yes. Cross out the constant.
That's, because that
You just
is
plug
the
it in.
exact same thing as that. And that would be good to write down. Okay. Alright. How we doing? What'd you guys get for number 2? 7. 7 for number 2. Let's look at that. My derivative, if this is f of x, I'll write it down again. F of x is 3x to the 4th minus 5x plus 2. The derivative function that I would get if I ran that whole thing through the limit definition of the derivative, I would get the derivative function to be 12x cubed minus, okay, this might have been the part that you weren't sure about because we didn't do one of those. 5x, remember 5x is like 5x to the first. So if I'm following the power rule, 1x to the 0, and anything to the 0 power is equal to 1. So the derivative of 5x is just a 5. Ironic thing on that one is if you put right 5x down, you would still get 7. So I would be looking at that. F prime at 1, 12 times 1 cubed minus 5, and that's 7. Yes. Sure. Here's the function, right? Are you okay with 3x to the 4th derivative? Okay, so you're okay with that. 5x's derivative is going to be 5. Okay? When I take the derivative of a linear term, a degree 1 term, you know, if it's y equals 10x, then the derivative is just 10. Okay? And if you think about it this way, the derivative is the measures slope. If you're looking at that, it's a line. The slope of that is always equal to 10. So its derivative is 10. Something like y equals x squared has different slopes at different points. And so we actually, when I asked to write the derivative function of that is a different, it's a function that's going to be changing for x. Okay. All right, are we good with? So then once we got that, we plugged in the 1 for x and we got the 7. Okay. All right, anybody else on example 2? Now, instantaneous rate of change. Is IRC, it's the derivative value. It's the slope of the tangent line. It's the same thing. It's another code. It's another phrase that's indicative that says, I need a derivative value. This question is asking you to find the derivative of f at, negative 1. F prime of x at x equals negative 1. When you do that, you have to write the derivative function first. You write the derivative function first, and then you evaluate it at the given value of x. So let's talk about this derivative. It's 1/2 times 4 times x cubed minus 2/5 times 3 times x squared plus 2. All right, take a look at that. That's me following my power rule and my constant multiple rule. So the derivative of x to the 4th is 4x cubed. I'll still have times 1/2. Derivative of x cubed is 3x squared, still times a 2/5. The derivative of 2x is 2. The derivative of x is 1 times a 2 is 2. You can think about that a lot of ways. So f prime of negative 1 is going to be 2 times negative 1 cubed minus 6/5. Oops, I'm going to run out of room here. Let me write this underneath here. Oh, give me an eraser, man. Troop. Come in. Hello, what can I do for you? Who is it? Hi. Oh, thank you. Oh, in my mailbox. Awesome. Thanks. Bye. Oh, can you take this for my car wash and return it? Thank you. I appreciate that. Okay. So this is going to be 2 times negative 1 cubed minus 6/5 times negative 1 squared plus 2. So 2 times negative 1 minus 6/5 times 1 plus 2, negative 2 minus 6/5 plus 2, big old negative 6/5. That means if I looked at the graph of this 4th degree polynomial at the point where x equals negative 1, the tangent line to the curve would have a negative slope. This 4th degree polynomial's graph, when x is negative 1, this is probably, I don't know if it's bumpy or not, but some 4th degrees are just kind of like flat parabolas. Parabolas are more flat on the bottom. So if we were looking at the graph of this 4th degree polynomial over where x is negative 1, over here where x is negative 1, we'd be looking at a negative 6/5 kind of slope to the line touching the curve. Right? That's what we're calculating. We're picking a point on the function and we're calculating the slope of a line touching that function at that point. That measures how fast the function is changing at that point. Instantaneous rate of change, slope of the tangent line, value of the derivative, all means the same thing. Okay. In example 4, it asks us for the equation of the tangent line. What's the function again? 3x squared minus 4x plus 5. So this was like the last thing we were doing in our notes last time with the limit definition of the derivative, was what it meant to write the tangent line equation. And we did talk about that part of that process would be determining the slope of the tangent line. How am I going to find the slope of the tangent line that I'm talking about in this problem? What do I have to do? I'm going to find the derivative of f and evaluate it at 1. I'm going to take the derivative of this. Remember, the slope of the tangent line is just code for value of the derivative or derivative value. So I need the f prime function, the derivative function for 3x squared minus 4x plus 5 at x equals 1. The other thing I told you we were going to need is a point. Now, we're typically given the x value to make our point. So we are told that I want to do the tangent line at the point where an x equals 1. Where am I going to get the y for this point? Plug in 1 where? Into the original function, right, f of 1. So you can see I'm going to need f prime of 1 to be the slope. I'm going to need f of 1 to be the y value of my point. I'm given x of 1. That's going to be the x value of my point. See if you can finish that. And write me an equation in our new favorite form, point slope form. A lot of the times when you're doing a derivative, you'll be doing something with that derivative. So I'll rarely just be like, hey, find me a bunch of derivatives. I'll be like, hey, find me the slope of the tangent line to this function. Hey, find me the instantaneous rate of change for this function at x equals 2. Hey, write me a tangent line to this function, which involves it. So all of those things involve a derivative, even if though they don't explicitly say that. Okay, point slope again is y minus y1 equals m times x minus x1. You right? Just so we're clear on everything. M is the slope, and the x1, y1 is the point.